Hello everyone. I hope you're having a good time learning about networks and systems. Many of you have submitted the first assignment. I was very happy to see that. And this short video is aimed at describing the solutions to the first assignment. So I've picked a few questions, important questions, which I think are very representative of the type of questions you might get in this class. And I would like to describe the way to go about solving them, the main steps involved in solving them. The exact solutions will be provided as a separate file in the portal as well, but this video hopefully will help you to learn about problem solving in this subject, which is quite important. Okay, so let me proceed. So if you look at the first assignment, there are quite a few questions, but there are many questions which go like this. A system is described first. What do you mean by describing a system? A very typical way of describing a system is to provide an input-output relationship, a mathematical equation which can be used to find the output when an input is given. So for instance, if you look at question number 2, it reads, a system with input x of t and output y of t is described by the relation y of t equals x of t plus 2. So that is a mathematical description of the input-output relationship. If the input signal is x of t, you are going to plug into this equation and you will get an output signal y of t. Okay? Now, that is a complete description of a system. If you know for every input how to calculate the output, you have already described the system entirely. So that is a precise and complete description. Once you have such a description, you can answer questions about properties of the system. So one question that is asked in question number 2 is the system linear or nonlinear? Now once again, the system is described by the equation y of t equals x of t plus 2, and the question that is asked is the system linear or nonlinear? So how do you go about solving a question like this? So let me take that up as an illustration. Okay, so let's look at this question number 2 in assignment 1. You have a system which is described by the input-output relationship y of t equals x of t plus 2. So the question that is asked is it linear or non-linear? Okay. So how do you go about answering such questions? So here's a little tip. All problems in this class will be quite simple in a certain sense. Okay. So there will be a certain definition for a property, and you will be asked to check whether that property is true. So this is a very typical way of doing it. So you've been given a system here, y of t equals x of t plus 2, and here's a property which is linearity of the system. So now the way to solve these questions is, first you have to read the mathematical definition of linearity of a system, and then apply that definition to the description of the system and find out if it is linear or not. That is the way to solve these questions. So many of you, if you look at this equation, you might want to intuitively answer this question, oh, it looks linear, it's non-linear, etc. But that's not the way to go about actually solving it. And system has been described to you, a property has a mathematical definition, you have to verify whether that definition is satisfied or not. That's the way to solve this problem. So what is the mathematical definition of linearity? For linearity, you have to check for two properties. First is additive and homogeneous. What is additive? Additive means if you have two inputs, x1 of t and x2 of t, and if x1 of t produces an output y1 of t and x2 of t produces an output y2 of t, the input x1 of t plus x2 of t should produce an output y1 of t plus y2 of t. This is the definition of the additive property. What is the definition of the homogeneous property? If you have an input x of t which produces an output y of t, and then you look at the input a times x of t, where x is in general a complex number, you should get the output a times y of t. Any system, any input output relationship for a system, if it satisfies these two properties, additivity and homogeneity, then that system is said to be linear. Okay. So, now we have a system here y of t equals x of t plus 2, and one needs to check whether both these properties are satisfied by this input output relationship. So, let us look at that. If you have, let us look at additivity. If x1 of t is the input, output I have represented it as y1 of t. So, now from the input output relationship, I know that y1 of t equals x1 of t plus 2, right. If x1 of t is the input, how do I find what the output is? You plug in x1 of t instead of x of t in the input output relationship, the answer you get is the output. Likewise, y2 of t is going to be x2 of t plus 2. Okay. Now, I have to say put question marks here because these things may not be true. I have to check if these two are true or not. I have to see if the input is x1 of t plus x2 of t, will I get the output as y1 of t plus y2 of t. So, now this is the definition of the system, right. This input output relationship is the definition of the system. Now, I have to use the definition to figure out what the output would be. That is what I have done here for y1 of t and y2 of t. Now, if the input is x1 of t plus x2 of t, what is the output going to be? If x1 of t plus x2 of t is the input, the output is going to be, instead of x of t in the definition of the system, I have to plug in the input that I have. The input that I have is x1 of t plus x2 of t. So, the output is going to become x1 of t plus x2 of t plus 2, right. According to the definition of the system, if x1 of t plus x2 of t is the input, the output you get is x1 of t plus x2 of t plus 2. Now, what is y1 of t plus y2 of t? Okay, we know what y1 of t is, it is x1 of t plus 2, y2 of t is x2 of t plus 2. So, y1 of t plus y2 of t is going to become x1 of t plus 2 plus x2 of t plus 2, and that is going to become x1 of t plus x2 of t plus 4. Okay. So, now one can compare these two expressions and say that these two are not equal. Okay. So, if I have two inputs x1 of t and x2 of t, and if I provide the new input x1 of t plus x2 of t, the output I get is x1 of t plus x2 of t plus 2, and that is not equal to the sum of the two individual outputs y of t, y1 of t and y2 of t. So, if these two are not equal, then the system that is defined by y of t equals x of t plus 2 does not satisfy the additivity property, and it is therefore not linear. Okay. So, this is the way to solve this problem, and any other definition of the system that is given to you, it could be slightly more complicated than y of t equals x of t plus 2. You have to follow a very similar approach. You have to check additivity and homogeneity, and you have to use the input output relationship of the system and check whether it satisfies those properties or not. Okay. So, let us look at a slightly more complicated type of question, which is say question number 3. So, here is a similar sounding question, but the systems satisfy more complicated input output equations. Look at the question here. You have a system with input x and output y, and which of the following input output relationships are linear? That is the question. So, if you look at the first situation, it says y of t times dy by dt equals 5 times x of t. So, now how do you determine whether this is a linear system or not? You have to follow an approach very similar to before. You have to write down x1 of t. So, for instance, you have to check additivity. How do you check additivity? You have to say x1 of t satisfies a certain equation with y1 of t, x2 of t satisfies a certain equation with y2 of t. Now, in this case, the equation is slightly more complicated. It is a differential equation, and you may not be able to find y1 of t and y2 of t explicitly in terms of x1 of t and x2 of t. In the previous question, we were able to do it. In this case, you may not be able to do it. Now, if you are not able to do it, it is not a significant difficulty, because you do not need the explicit form for y1 of t and y2 of t. What you really need is whether additivity is satisfied or not. So, let us see how to work with a situation like that. So, to illustrate that, let me take the first choice here and show you what would happen if you were to look at that. So, question number 3, the first choice says y of t dy of t by dt equals, let me just look it up, it is 5 times x of t. This is the input output relationship. Okay. Now, if x1 of t is the input, then the output y1 of t satisfies y1 of t dy1 of t by dt equals 5 times x1 of t. Now, if the input is x2 of t, then the output y2 of t satisfies y2 of t by dt equals 5 times x2 of t. On the other hand, if the input is x1 of t plus x2 of t, then let us say the output corresponding to this, we need a notation for that. The output corresponding to this, let us say, is I will call it y tilde of t. Okay. Then you will have y tilde of t d y tilde of t by dt equals 5 times x1 of t plus x2 of t. Right. If input is x1 of t plus x2 of t and the output is y tilde of t and x1 of t plus x2 of t satisfy this equation. So, if you put in, instead of x of t, if you put in x1 of t plus x2 of t, and instead of y of t, if you put y tilde of t, you should be able to satisfy this equation. So, now the question is y tilde of t equal to y1 of t plus y2 of t? That is the question we are asking. If we can show in general y tilde of t is equal to y1 of t plus y2 of t, then we know that the system is additive. The input output relationship satisfies the additivity property. Now, we have to plug in this, now we have to check whether this is true or not. How do you check whether this is true or not? I know y tilde of t satisfies this equation. Okay. So, let me try and evaluate the left hand side by substituting y tilde of t equals y1 of t plus y2 of t. Now, if it were true to be equal, then the right hand side should work out to 5 times x1 of t plus x2 of t. So, that is the way you check whether additivity is true or not without really solving explicitly for y1 of t and y2 of t. You can check if an equation involving y1 of t and y2 of t is satisfied or not. So, let us plug in y tilde of t equals y1 of t plus y2 of t into this equation on the left hand side and use the previous equations and see if we get the same thing as the right hand side or not. Let us try that. Y1 of t plus y2 of t, okay, d by dt of y1 of t plus y2 of t. Okay. So, we know how to simplify these terms. You do the differentiation, multiply, etc. You are going to get y1 of t dy1 of t by dt plus y2 of t dy2 of t by dt. And then interestingly, you will also get cross terms, y1 of t dy2 of t by dt plus y2 of t dy1 of t by dt. Right. So, one can take this part of the expression, now use this equation. I know this is equal to 5 times x1 of t. Similarly, you can take this term right here and use this equation. I know that is equal to 5 times x2 of t. On the other hand, these two terms cannot be simplified any further. So, those two terms still show up. Okay. On the other hand, what happens if you put in y tilde of t in this equation? Y tilde of t dy tilde of t by dt equals 5 times x1 of t plus x2 of t. Now, if you look at these two equations, y1 of t plus y2 of t satisfies this complicated equations with these mixed terms. On the other hand, y tilde of t dy tilde of t by dt is simply equal to 5 x1 of t plus 5 x2 of t. So, clearly the answer is y tilde of t is not equal to y1 of t plus y2 of t, right. If y1 of t plus y2 of t is equal to y tilde of t, this right hand side would have simplified to 5 times x1 of t plus 5 times x2 of t. These two cross terms will not have been there. Since the cross term showed up, clearly y tilde of t is not equal to y1 of t plus y2 of t, which means this equation is not additive, in which means it is nonlinear. Okay. So, like I said before, given an input-output relationship, you plug in these definitions of these properties, look at how to substitute them into the equation, test if the additivity property is satisfied, and you get your answer. Okay. So, that is how you go about solving these kind of problems. And so, let me make a few more comments about linearity, etc. So, let us go back and look at the third question. Now, if you look at the third question, I did some calculations to show that the first choice is nonlinear, and if you repeat the same kind of argument for the other choices, you will get that the second choice is in fact linear. Okay. The third choice will once again be nonlinear, and the fourth choice will be linear. Okay. So, you can go ahead and think about it and write down the exact steps that I wrote down for the other problems, and you will be able to show that linearity holds for both the second and the fourth choices. Remember, you have to check both properties for linearity, both additivity and homogeneity. I only showed checking of additivity, you also have to check the homogeneity property, that is very important. Okay. And you can do that, but there are some general rules of thumb to remember. If you have an input-output relationship, and that input-output relationship involves a product of terms or a squaring of terms. So, for instance, here is a y square of n, and here is a product y of t times dy of t by dt. Okay. If it involves a product of input-output or product of output with some derivative of it, or any product of that form, for instance, y square of n itself is a product of y of n with y of n, right. If it involves any product, taking products of inputs and outputs is not a linear operation. So, that is a hint for you that the first and the third are going to be nonlinear. On the other hand, if you look at second and fourth, you do not have any products of inputs and outputs. You might ask me, there is a product of t times dy by dt, but that is not a problem. If you have the independent variable multiplying the input or the output, that is not a problem. The independent variable is t, and that is not really going to affect the input-output linearity or nonlinearity if it multiplies with the signal or its derivative, or the output or its derivative. If y on the other hand multiplies with itself, then it affects the linearity. So, this is a good rule of thumb to remember, but that by itself is not a proof. If you want to show that something is linear or nonlinear, you have to write down the equations like I did and prove it. Okay. Now, there were lots of interesting questions in the forum also about linearity and homogeneity and additivity. It turns out there are additive systems which are not homogeneous, and there are homogeneous systems which are not additive. There are some examples, interesting examples, which you can use, and maybe I should highlight one of them to show you how both of these are possible, just to give you a little hint as to how this works out. For instance, here is an example. If you have a system y of t is real part of x of t, it turns out this guy is additive but not homogeneous. Okay, so think about it. If you multiply a times x of t, and if a is complex, it is not the same as multiplying a complex number with the real part, and clearly it will not be homogeneous. On the other hand, it will be additive. x1 of t plus x2 of t will give you the sum. And here is another interesting system, which is x square of t by x of t minus 1. Okay. This guy, it turns out, is homogeneous but not additive. Okay. So, instead of x of t, if you put in a times x of t, you see the a square on top will cancel with the a at the bottom, and you will get back a times the output. So, it is homogeneous, but clearly it is not additive. I gave you the rule of thumb about products, and there is a product and a quotient, x square of t divided by x of t minus 1. Clearly it will not be linear, but it will not be additive. It is easy to show that, but it is homogeneous. Okay. So, both these conditions are kind of independent of each other, and you have to check both. In any question, you have to check both. Okay. So, that is an interesting little tidbit about linearity and homogeneity, etc. Okay. All right. So, let us look at a few other questions. Okay. So, that is the third question, and the fourth question I believe is very similar, but you are asked to check for time invariance and time variance. Okay. So, now once again let me maybe show you one way of checking for the main method for checking for time variance and time invariance, and maybe we should do one question of that type. Okay, so we are going to talk about time invariance next, and for time invariance, for instance, question number 4 in your first assignment is about time invariance, and it has quite a few complicated examples. So, I am going to start with a very simple example. Look at the system we had in one of the earlier questions, y of t equals x of t plus 2, and ask the question. We saw that it was non-linear, and ask the question whether it is time invariant or not. Is this time invariant or time variant? Okay. So, how does one solve such questions? Remember, the definition for time invariance is quite simple. If x of t produces an output y of t, x of t minus t naught should produce an output which is y of t minus t naught. Okay, this is the definition for time invariance, and one needs to check that. So, if x of t produces an output y of t, I know that my output x of my input and output x of t and y of t satisfy this equation. Okay, so y of t is x of t plus 2, I know that. Okay, right. Now, if x of t minus t naught is the input and the output is y tilde of t, I know y tilde of t equals x of t minus t naught plus 2. Okay. Is that right? So, the question now is y tilde of t the same as y of t minus t naught? Okay. So, the question is y tilde of t equal to y of t minus t naught for every t? That is the question. So, how do you answer that? You try to find y of t minus t naught. How do you find y of t minus t naught? I know y of t is x of t plus 2, this equation is true, right. Here instead of t, I need to replace it with t minus t naught. So, if I do that, I see that y of t minus t naught is the same as x of t minus t naught by plus 2, and that, as it turns out, is the same as y tilde of t. So, it turns out this input output relationship defines a time invariant system. We saw that it was not linear, but it is time invariant. Okay. So, let me take another simple example to illustrate how you go about finding time variant or time invariant systems. Here is the other example, y of t equals t times x of t. Okay. So, it turns out if the independent variable t appears by itself in the input output equation, that is one of the hints to show that it is a time variant system, it is not a time invariant system. Okay. The independent variable, if it appears by itself in an input output equation, that is a hint pointing towards a time variant system. Okay. One can check this very easily. If x of t is the input and it produces y of t, we know that y of t satisfies this equation, t times x of t. Now, if x of t minus t naught produces an output y tilde of t, we know that that satisfies t times x of t minus t naught. Okay, remember that is the equation. If input, so if I say my input is x of t minus t naught, how do I find the corresponding output? I have to take that input x of t minus t naught and replace, instead of x of t in my input output equation, I should put x of t minus t naught. I am not allowed to touch anything else in the input output equation. Okay. So, keep that in mind. If I have an input output equation involving an input signal x of t and I want to find the output corresponding to the input x of t minus t naught, instead of x of t, wherever you have x of t, you have to put x of t minus t naught. You should not change it to anything else. A lot of people invariably end up saying, even if my input is x of t minus t naught, they end up saying the output will be t minus t naught times x of t minus t naught. That's not what this input output equation says. This input output equation says y of t equals t times x of t, which means if the input is x of t minus t naught, instead of x of t, you should put x of t minus t naught. Okay. It is not the same as changing t by t minus t naught. Keep that in mind. Okay. So, a y tilde of t is t times x of t minus t naught. On the other hand, what is y of t minus t naught? How do I find what y of t minus t naught is? I have this equation for y of t is t times x of t. Now, how do I find y of t minus t naught? Instead of t, I should put t minus t naught. That is the definition of, that is the meaning of this equation. If I say y of t is t times x of t, instead of t I have to put t minus t naught to get y of t minus t naught. So, there I will get t minus t naught times x of t minus t naught, and you see these two are not equal, and this input output equation is time variant. Okay. So, like I said, a very good hint is to look at this independent variable. If the independent variable appears by itself in the input output equation, then it is going to be time variant. This is a very useful hint, and many questions one can use this and quickly solve the problem, otherwise you will be going you will be repeating these calculations. Here is another example which is quite involved, and sometimes people end up mixing it up. So, I wanted to show you this example. Let us look at x of t, y of t equals x of 2t. Here is another interesting input output equation, and let us try to find if it is time invariant or time variant. Once again, what is the way to do it? If input is x of t, your output is going to be y of t, and that y of t satisfies this equation. Now, I want to find if input is x of t minus t naught, what will be the output? Okay. So, this is a bit of a slightly confusing question. Okay. So, I have x of 2t here and I have x of t minus t naught. Okay. What will be the output for y tilde of t? Okay. So, think about it, the correct answer is it is x of 2t minus t naught. Okay. Remember, why is this true? What do I mean by x of 2t? Okay. Everything boils down to what I mean by y of x of 2t. Okay. If I give you x of t as the signal, x of t is some signal or a function of one variable, as they say. X of, to find x of 2t, what should you do? What is x of 2t? Wherever you have t in the expression for the signal, I have to put 2t. That is what this means. When I say x of 2t, that is what I mean. Wherever I have t, I should substitute 2t. So, for instance, x of t could be, I do not know, t plus 2 whole squared. Okay. How do I find x of 2t? Wherever I have t, I should put 2t. I should not touch anything else. I am not allowed to touch anything else, right. So, x of t is some function of t. What is x of 2t? Wherever I have t, I should put 2t. Excuse me. Now, the question that is being asked here is x of t is x of t minus t naught, right. The input x of t, the function x of t is x of t minus t naught. What is 2t? Instead of t, I should put 2t. So, I get the output y tilde of t being x of 2t minus t naught. Think about this once again. This is the meaning of x of t minus t naught being input to the system. Instead of x of t, I should think of it as x of t minus t naught. Now, my signal has become x of t minus t naught. How do I find x of 2t? Wherever I have t, I should put in 2t, and that is what I get the answer. On the other hand, y of t minus t naught is what? I have an equation for y of t. Y of t is x of 2t. Wherever I have t, I have to put no, I am sorry, y of t is x of 2t. Okay. Instead of t, I should put t minus t naught. On the right hand side, instead of t, I should put t minus t naught, and I will get something like this. Okay. So, you see these two are not equal, and this is a time variant system. So, once again, this is another useful hint to have. If you have constants multiplying the input variable in the independent variable inside an argument, if you have constants inside an argument, it's not going to be time invariant. Okay. So, the only trick here is the definition of functions, independent variable, dependent variable. What is the meaning of saying the input to my system is x of t minus t naught? Okay. So, what do I do when I put y of t minus t naught? So, how do you evaluate these things? How do I compare? There are some definitions here. Think about what I wrote down here in the example, and you will be able to solve these problems. Okay. So, that is the discussion on time invariance. And if you go back to your fourth question, you see if you use the rules I told you. So, first question has t appearing by itself, third option has n appearing by itself, that is again the independent variable, and the fourth option has t appearing by itself, again an independent variable. So, the first, third and fourth are time variant, they are not time invariant. The second one on the other hand has no problems, it is a time invariant system. So, one can quickly do this. Okay. So, I am going to skip the causality question, it is as it turns out the answers are first and third, and which of the questions are real, which of the following signals are real, it is again an easy definition of the real number system. A useful hint is a number x is real if x equals x conjugate. Okay, that's the way to check if some complicated function is real or not. Okay, so if the number is given to you, you can quickly say if the imaginary part is 0, but sometimes it might be a complicated way in which the imaginary parts add together and become 0. Okay, so it may not be easy for you to check, but a useful definition for real numbers is x equals x star. If a number x is real, then x is equal to x star. Okay, the conjugate of x is equal to x if and only if x is real. Okay, so one can use that, and quickly you will see immediately you will settle that this guy is real, right. If you take a conjugate, what happens? You get e power minus j2t, but then the second term becomes e power plus j2t and is the same as the first one. Okay, on the other hand, other two guys will change if you take conjugate. Okay. The next question is about smoothness of signals, okay, which is a continuous signal, which is discontinuous, etc. Okay, so in this class we are not reviewing calculus too much. In the first week's lectures, we pointed you to a lot of nice web pages on continuity of functions, basic calculus. I will urge you to go and look at it. It's not a very hard area, but we are not going to spend too much time on it. In general, a very simple layman's definition is if in the plot of the signal you have any jumps, then it's discontinuous. And if in the plot of the signal you have any corners, then the derivative is discontinuous. Okay, so what do I mean by that? Let me just quickly show you a couple of examples and then we'll proceed. Okay, so a good simple rule of thumb for if you don't want to get complicated with definitions. Okay, so here's an example of, let's say, a discontinuous function. If you have a step like this, okay, this is a point of discontinuity. Okay, discontinuous at this point. If you have a corner in your signal, what do I mean by a corner? Something like this. Okay, if you have a sharp corner, a point where the function takes shape, here it's continuous. Okay, the function continues to be continuous as in there is no jump, but then there is a corner, which means the derivative will be discontinuous here. Okay, so think about why this is true, and this is a hint you can use quite often to figure out whether or not the function is continuous or discontinuous, and whether the derivative is discontinuous or not. For instance, one of the questions that were given is say sin t u of t. If you sketch this guy, you're going to get, it will be 0 throughout on the left, and then it will start right here and go like that. So you can notice that this is a continuous function, there is no problem with continuity, but then here there is a sharp corner. Okay, it takes off like that. So the derivative is going to be discontinuous at that point. Okay, so this is the only hint I wanted to give you on discontinuous and continuous functions. I'll urge you to look at all the notes that we pointed you to in the week zeros material on continuity, discontinuous, derivatives, etc. It will help you gain a deeper understanding of where all these things are coming from. Okay, and the next type of question you have in assignment 1 is evaluating values for the signal. I'll let you do that. It's not very hard. If you look at this question, you simply have to put t equals pi, and remember that e power j pi, you remember the unit circle definition I gave you for e power j theta, right? So that's a very powerful definition to use. If you simply use that, e power j pi, you will see is minus 1. And what about e power minus j pi? Okay, whether you do plus pi or minus pi, you hit at the 180-degree angle, so you get minus 1. So you use e power j pi, e power minus j pi is minus 1. You can solve the 8th question. There's no more, nothing more to it. Okay. The 9th question is on periodic signals. So let me spend a few minutes on periodicity and how to go about working with that. Okay. So periodic signals. So there are some pitfalls here, but usually it's not too hard to worry about it. Okay, so there are some pitfalls in the definition of periodic signals, but usually it's not too hard to check if a signal is periodic or not. In many cases, it's easy to do that. So the definition of periodicity is the following. Okay, a t greater than 0 is said to be a period, okay, so let me define it a little bit more carefully, is a period of x of t if x of t plus t equals x of t for all t. Okay. So, that is the way to think of periodic signals. There is the time period of capital T over which the signal has to be looked at, and after that for every other t it simply repeats. Okay, x of t plus t is the same as x of t. So, if you know x of t from 0 to t, you can simply repeat that from t to 2t, 2t to 3t, minus t to 0, minus 2t to t, minus t, etc., and then get the entire x of t. So, it goes from minus infinity to infinity, but only a period of t really matters for a periodic signal. Okay. So, that is periodicity, and this greater than 0 is a bit of a technicality and it is important. Okay. So, t greater than 0, it cannot be equal to 0, because for equal to 0 every signal will satisfy this. So, it is a very technical kind of definition. Okay. So, there is something called a fundamental period. Okay. What is the fundamental period? The smallest t for which t is a period. Okay. So, I mean I am not making a technical definition, but hopefully you understand what I am saying. So, smallest period of a periodic signal is said to be the fundamental period of the signal. Okay. So, these two definitions are the definitions to use. You have to check if t is a period, you have to simply plug in t plus t instead of t in x of t and see if it evaluates the same as x of t. And for the fundamental period, you have to find what is the smallest valid period for a signal x of t. And there are some nuances here, but this is the definition, and with this definition if you go in and look at your problem, if you look at the 9th problem, you can quickly see check the answer. Which of the following signals is periodic with fundamental period 2 pi seconds? Okay. So, the easy questions, easy parts are second and third option. Okay. So, if instead of t here you put t plus 2 pi, you notice that there is a e power t term which will become e power t plus 2 pi. Okay. And here again there is a e power t term which will become e power t plus 2 pi. Okay. And of course, there is a e power j t which will be the periodic part, but then there is the e power t part which will make t plus 2 pi not the same as x of t. Okay. So, in this equation if you put t plus 2 pi instead of t, you will not get the same form again. So, this is not periodic at all. Okay. So, and the same thing will hold here, there is this e power t guy showing up and does not cancel, and that will make it aperiodic. Okay. So, the fourth option on the other hand is just e power j t, and you know that e power j 2 pi is equal to 1. Okay. So, instead of t if you put t plus 2 pi, you are going to get e power j t times e power j 2 pi. Same thing here, e power minus j 2 pi, both of them will become 1, and this will evaluate to exactly the same form. I am not writing this down in great detail, hopefully it is clear to you. Okay. So, now if you look at the first choice, this is a little bit more interesting. It turns out 2 pi is a valid period for this signal. Okay. If you put instead of t, if you put t plus 2 pi, you will get the same form again. So, it repeats at 2 pi, but it turns out it is not the fundamental period. Okay. Instead of t, if you put t plus 2 pi over 3, okay, the 3 and 3 will cancel, but still the 2 pi remains and you will get the same form again. Okay. So, the fundamental period for this guy is actually 2 pi over 3, it is not just 2 pi. Okay. So, this is a periodic signal, but the fundamental period is not 2 pi. So, that is why the first option is not correct. Okay. So, one can evaluate this and find out whether it is periodic or not. Okay. A useful question to ponder about is whether a DC signal is periodic or not. Okay. Suppose you look at a DC signal, it is just flat, it is periodic or not. It turns out for every value of t which is non-zero, the DC signal is periodic with that period t. Okay, that is true, right? X of t plus capital T is going to be equal to x of t. But then what is the fundamental period of the DC signal? Okay, if you think you know the answer, do post it on the forum. It is an interesting little question to ponder about. Okay. Okay. So, the 10th question is on complex frequencies. There was a question once again asked in the forum about what is the complex frequency? It's actually a relatively simple definition, and don't get confused by the term frequency. It's a frequency is just used for legacy reasons here. Complex frequency is just more or less a notation. Okay, if you have e power st where s is complex, s is called the complex frequency of that term. That's the simple notational definition. E power st where s is complex, s is called the complex frequency of that term. So, in this equation you have e power t times cos phi t plus pi by 6. So, now we need to replace cos with the exponential form. Okay, so, let me maybe do this alone real quick. Okay. So, if you look at the term there, it says e power t times cos. So, this is question number 10. X of t is e power t times cos 5t plus pi over 6, right. So, now one can write this as e power t times e power j 5t plus pi by 6 plus e power minus j 5t plus pi by 6 divided by 2. So, write cosine in terms of e power j theta plus e power minus j theta by 2. Okay. So, once you do this, you can multiply it out. You see you get e power 1 plus 5j times t times some complex number e power j pi by 6 plus e power 1 minus 5j times t times another complex number e power minus j pi over 6, the whole thing divided by 2. So, what complex frequencies are present in this? Once again, what is the definition? If e power st is present in your signal, s is the complex frequency. That is all. That is a, it's like I said, it's a notational definition, doesn't have a physical meaning. Be very watchful of that. Okay. So, what are the e power st terms here where s is complex? You have a 1 plus 5j and a 1 minus 5j, and that's it. Those are the complex frequencies in this signal. Okay. And let's move over to the next question. That's question number 10, and 11 and 12 are very nice questions. These are about the ramp and the unit step, and how to represent a signal in terms of the ramp. Okay. So, let me maybe spend a couple of minutes on that. Okay. So, now we studied this basic unit step function u of t, which has several forms. One can write it in various forms. I am going to just pick some form which may not be the best form. So, maybe I pick this guy. U of t is 0 for t less than 0 and 1 for t greater than or equal to 0, and then r of t has this very simple form t times u of t. So, the sketch is quite interesting to keep in mind. 0, it goes up to 1 and stays at 1 forever. Okay. So, that is u of t versus t, and r of t versus t starts at 0 and goes off at 1 at a 45-degree angle towards infinity. Okay. So, that is r of t. Okay. So, now it turns out many signals in practice, okay, can be written in terms of a combination of u of t and r of t. These are quite valuable in many systems. Your signal is either going to jump from 0, stay at some value, and then change some other value, change some other value. It's either going to be piecewise constant or piecewise linear. It would start somewhere, grow up linearly to something, and then come down. Or that's how most signals are. They are piecewise constant or piecewise linear. Okay. So, any such signal, piecewise constant, piecewise linear signals, can be written as a combination of u of t and r of t, maybe in multiple ways. Now, why is that very interesting in practice? Because once you write it as a combination of u of t and r of t in LTI systems, if you know the unit step response and the unit ramp response, so to speak, or even unit step response good enough, you know how the final signal is going to look like. So, given the input signal as a piecewise constant, let us say, you might be able to roughly sketch how the output would look, and you will have an intuition of how your system is working based on some simple ideas. Okay. So, that is why these things are very important, and one very good piece of exercise is to take some piecewise constant signal and write it as a sum of shifted and scaled unit steps and unit ramps. Okay. So, that is a very good exercise, and the last two questions ask you to do that for ramps. One can also do for unit step and all that. Okay. So, here is an example for unit step, maybe a slightly non-trivial example. Okay, so let's say somebody gave you a function like this. It stays at -5 up to, let's say, 5 and stays a constant after that. Okay, so how would one write this? This is basically, think about it, it's u of 5 minus t, is that right? It's u of minus t, and then it's been shifted right by t, so you have u of 5 minus t, and then you have to multiply by minus 5. Okay. So, this is a signal which is again piecewise constant, it stays constant at minus 5 and then it comes down to 0. So, this would satisfy this equation. So, you have several such things. So, for instance, one might want to write something like this. You stay at 1 for a while, and then at maybe time 2 it moves off to 4, moves off to 2, and then maybe at time 3 it comes down to minus 2, maybe minus 2, and then maybe comes down to 0 at time 4 and stays like that. Okay. So, here is a signal which actually might be an input signal to some system that you build. It's quite realistic. Quite often many signals look like this. So, for such a signal, how would you write it in terms of shifted unit ramps? It's unit signals, it's unit steps, it's possible. How do you do that? So, this one would be u of t, okay, plus u of t minus 2, okay, minus 4 times u of t minus 3 plus 2 times u of t minus 4. Think about how I did that. One can sketch each of these things, separately in a separate page, okay, and then see how it ends up adding to give you what you want. Okay, so this is an important step. This is not very hard to do, but hopefully you've seen how this is done. Okay, so this is in terms of unit steps, and what is being asked in your question is unit ramp, right? So, if you go out to the last couple of questions, okay, you are asked about writing a signal like this, which starts at minus 2 and increases up and in a certain slope such that at 0 the value is 1. Okay, so that's the signal, and you have to write it in terms of the unit ramp r of t plus b divided by a. So, if you look at it very carefully, r is it's a shifted ramp and it's also scaled. Okay, so it's multiplied by something. Okay, so one can think about this very carefully, and if you want, you can do some careful calculations. But let me just give you the answer here and explain how I got to that answer. If I start at minus 2 and then you have a signal like this, which at 0 crosses 1. So, now look at what a ramp is. The unit ramp just does this. Okay, so, it starts at 0 and goes at a certain angle. This thing is starting at minus 2. So, the first thing is to shift the ramp left to minus 2. How do you shift a signal to the left? Instead of t, you put t plus the shift. Okay. So, if I do that, I am going to get a signal like that. Okay. This guy is r of t plus 2. Right, this guy was r of t, this guy is r of t plus 2. Okay, you have shifted it left by 2. Now, if you do a ramp, if you shift the ramp left by 2, what will be this value? This value is going to be 2, but in my signal I want that value to be 1. Okay, so that tells you what you have to divide by, and that tells you have to divide by 2 again. You divide by 2, you are going to get back to 1. So, this signal will be r of t plus 2 divided by 2. So, it is an easy calculation to do. One needs to think about it carefully and you will get the answer. Okay. So, that is the answer for the ramp question. And the next question is again a little bit more interesting. This is the last question. Okay, it goes like this. You have it starts at 2, increases linearly up to 1, and at 1, I'm sorry, at 1 it doesn't drop down like that, I'm sorry. It stays flat after 1, after 3 at 1, right? That's what happens. After 3 seconds, it stays flat at 1. So now this signal, once again, it starts at 0 at 2 and goes off increasing in a slope. Now that tells you it's going to be r of t minus 2, right? What is r of t minus 2? It starts like this and it keeps on going forever. Okay. Now I want to bring it back. To bring it back down and make it flat, I have to subtract off something, and what you have to subtract off, it turns out, will start from here and go in the negative direction, and that would be minus r of t minus 3. Okay, the ramp shifted right to 3, and then there is a subtraction to subtract out. Now if you add these two guys, you're going to get a flat signal. One is increasing at slope 1, another is decreasing at slope 1. You add these two guys, they cancel and give you something straight. So this is going to be r of t minus 2 minus r of t minus 3, and you're done. Okay, so if you do r of t minus 3, you would get something like this, right? This would be r of t minus 3, this is r of t minus 2. You subtract these two beyond this point, it's going to stay flat. Okay, so these two are parallel lines going like this. If you keep subtracting, you're going to get the same value of 1, and that's going to stay a constant. Okay, so it's useful, like I said, to write piecewise linear or piecewise constant functions in terms of r and u, and then if you know how your system reacts to r and u, you know how your system reacts to any input like this. So this is a valuable thing in practice. Okay, thank you very much. That was a description of the assignment 1, the questions on assignment 1. We'll also put up the solutions on the portal. Do have a look at it and keep solving problems. You'll really learn all about this subject quite well. Thank you very much.